In the previous video, we spent a bit of time looking at the input files for CrystalGrower and how you edit them manually. And we covered an example of using the standalone CrystalGrower Executable program. In this video, I'm going to spend a bit more time looking at how you input free energies of crystallization when using the standalone CrystalGrower program. So I'll just open my input.txt. And you can see we're going to run another simulation on barite. But this time I want to give it different free energies of crystallization for the interactions. So the first thing I'm going to do is change the name of the simulation to 3 barite so it won't overwrite my previous simulation. And save it. Then I'm going to go back to my net.txt file. If you remember from the previous video, this is where you specify the energies for your interaction types. So we've got interaction types 1 to 5 in our barite crystal structure. But what do these interactions correspond to? We can actually use Topos Pro to look at these interaction types, as this file was generated using Topos Pro. So here I've got the CIF file that the structure and bonds file I'm using for my simulations originated from, and I've calculated the simplified net, which has placed dummy atoms at the centers of the ions that I'm looking at, and I've added the interaction types on top. If you want to know how to visualize structures like this, have a look at the series of videos on using Topos Pro with CrystalGrower. So the interactions here correspond to the interactions in the net.txt file. So you can see we've got interaction type 1 here, 2 here and here, 3 here and here, and then 4 and 5. And you can also see that the numbering is the same in both directions. So interaction type 2 on the barium connects to interaction type 2 from a sulfate. That doesn't necessarily mean the energies are the same in both directions, as depending on the solubility of your ions, the free energy of crystallization can be different in each direction. So now we have some sense of what these interactions actually correspond to, we can start to change the energies. So for example, we can see that interactions 1, 2 and 3 are all bidentate interactions, as in there are 2 oxygens from the same sulfate binding to the same barium. So let's try increasing the energy for these interactions and decreasing the energy for the single bond or monodentate interactions and see what morphology we get. So I'll go back to my net.txt. And if you remember from the previous video, these energies gave us a plate-like structure with 001 facets and 4210 facets. So let's try increasing this interaction type 1 here so it matches interactions 2 and 3. So an easy way to do this is to just do find and replace. So I'll replace this 1 kcal per mole with 4 kcal per mole. And say replace all. And then save this net.txt file. Now if we leave all the other parameters the same, we'll be able to see the effect of changing that interaction on the crystal morphology. So let's now run our simulation and respond to the questions that appear with the same answers we did previously. Now that our simulation's finished, we can have a look at how this has affected the crystal morphology. So if we open our simulation from last time, we have our plate. And if we switch to the new simulation, you can see we've gotten a lot thicker in the 001 direction. So changing that 1 interaction energy has dramatically changed the growth rate in the C direction, or the 001 direction. So I mentioned earlier that the barium to sulfate connection isn't necessarily the same as the sulfate to barium connection. So let's try running a simulation now where we change that and see how that affects the morphology too. So I'll go back to my input.txt. And this will be simulation number 4, and then we'll go to our net.txt. We know there are 8 species in this unit cell. You can look at this in the structure file. And you can also tell from the net.txt, as there are 8 repetitions of interactions. So if we scroll down to the bottom half of the file, you can see that this label here changes to 1b, and that this is corresponding to the barium to sulfate bonds, whereas 1a was corresponding to the sulfate to barium bonds. So let's try changing these free energies of crystallization for these interactions and see how that's going to affect the crystal structure. So let's, for example, halve these strong interactions here down to 2 and double these interactions up to 0.6. And we know that these need to be the same for all the barium to sulfates. They can't be different because they're all crystallographically the same. So we'll make sure all of those are consistent. Now let's try running our simulation again. See if we get a different result. We answer the same questions again. and let our simulation complete. So now our simulation is complete, we can again visualize this in a veto. You can also use the CrystalGrower visualizer for visualizing these structures too. That will let you look at the actual molecules that make up the structure rather than spheres which you see in a veto. There are some other videos which show you in detail how to use the CrystalGrower visualizer. So if we switch now between our two previous simulations to compare them, you can see that a simulation where the energies were equal is quite smooth and symmetrical, whereas when they're both different, the surface is a lot rougher. The general morphology has stayed roughly the same though, aside from these corner facets growing a bit larger. This has shown you how to change the free energies of crystallization for net structures when you're not using the graphical user interface. It is slightly different and you have to be more careful about changing the interactions, making sure they're consistent through the file, whereas the user interface would do this for you automatically, but the process is generally quite simple. So now let's switch over to a tile-based structure and see how we can change the free energies of crystallization for the tiles. We don't actually need that net.txt file. We enter these ourselves when we're actually running CrystalGrower, but I'll go through an example with LTA, or zeolite A. So we need to make quite a few changes to our input.txt if we're going to run a simulation of a tile-based structure. An obvious one is to change the name of our simulation, so instead of 1_barite we'll have 1_LTA. We also then need to use a different structure file, so we need to find a structure file for LTA. So I've also got one in our structure files folder here. It's in the zeolites folder and it's called LTA_LTA PBT1. So I'll copy that file name and I'll go back to our input.txt and I'll change the location of the structure file. So it's in the folder called zeolites, and then I'll paste the file name here. So it's now looking for the correct structure file, but we also need to tell it that it's a tile structure, not a net structure. We also need to change the temperature at which it grows, because you don't tend to grow zeolites at room temperature. They're usually a lot higher, so I'll put 160 degrees Celsius for example. And as we're dealing with cages, generally you need to put your delta mu a bit higher to make sure that your structure will nucleate. So I'll set this to 100 just to make sure that my crystal starts to grow. We also can't use the same coloring we used for barite because the files are going to be completely different. So in this case we'll run a find simulation. So we'll just get rid of this line here. It won't be red anyway unless we type color, but just for consistency we'll omit it for now. I'll also change the delta mu mode to mode 3, because a key thing with tile structures is that our 0 for our delta mu is defined as the bulk crystal energy level, not the kink site energy level, as for net-based structures. So whenever we're modeling a zeolite or framework structure, we need to first find what this kink site level actually is, and we do that by finding the equilibrium point by using mode 3. So now we can save that and we can run our simulation. So let's double click our executable and we'll get a few different questions. So the first question, do you want all the QN scaling to be the same? This is related to the vertices of your natural tiles that make up your structure. So if you have some vertices with a lower coordination than 3 for open cages or open tiles, then you can change the energy scaling or energy penalty for each of these missing vertices. But LTA doesn't have any Q2s, it's only Q3. It's a closed cage or closed tile based structure. So we can just put this as yes. Now we get to the point where we can start changing the free energies of crystallization for our tiles. So we can either say that we want them all to be treated the same, or we can treat them all differently. So in this case I'm going to treat them all differently and press no. If I respond with no, I then get to assign free energies of crystallization for each of the condensation steps for one of these cages. So I control them all independently. So this first step here, I'm going to give an energy cost for each missing degree of condensation from our T-cube tile. This is also called the double 4 ring in a lot of zeolite papers. Because this tile is quite small, I'm going to assign it quite a high energy penalty, so 8.0. We know these numbers from research previously, so they might seem a bit random, but we found these through a series of thousands of simulations. And then our second cage, TTOC, that's also called the soda-like cage or the beta cage. I'm going to assign that a 5.4 kcal per mole penalty for each missing degree of condensation. That's the second smallest cage. And then we'll move on to the final cage, which is TGRC, also called the alpha cage or the LTA cage. This is the large cage which defines the largest pore in the system. We'll assign this an energy penalty of 1.0 kcal per mole for each missing degree of condensation. Then we're asked baseline energy separation without scaling. So this is a scaling factor. So whatever number we type in here, all those numbers that we just typed in will be multiplied by it. So in this case, we don't want to multiply. We'll just put it as 1.0 because we've assigned all the cage's energies independently ourselves. This parameter is mostly useful when you answer yes to the previous question. So if you want all the tiles to be scaled by the same energy, you can just put in 2.0 to this question and it'll space out the ladder reasonably to start with. It's a good first approximation. If we press enter here, we've now assigned the free energies of crystallization for our solid phase, similar to what we did with our net.txt. Now we're going on to defining the solution phase or the delta mu phase. So I'll put 100,000 steps, same as what we usually do for equilibration steps, and 500,000, so half the simulation at high supersaturation. And we'll just say find for the surfaces. And then we'll wait for our simulation to complete. So now our simulation's complete, we can visualize this structure. This time I'm going to use the CrystalGrower visualizer as it lets you look at the individual tiles that make up the structure. So I'll just load up the structure in CrystalGrower visualizer and I'll open the data file first, which contains the tile shapes that make up the structure. So that's this .viz file here. And it'll tell you it's loaded 5 tiles. Then we need to load the coordinates data, which will be our XYZ file. And you can see we've now got all the tiles drawn and coloured based on the layers. We can also switch to looking at the tiles as their type. That'll just be coloured based on what tile type they are. And we can also switch to looking at them as spheres, similar to what you'd see in a veto. The spheres in the CrystalGrower visualizer are sized based on the tile size, but you can also switch them to an average sphere size, which is more like what you'd see in a veto. There's another series of videos explaining how to use the CrystalGrower visualizer, but how much of an effect does the free energy of crystallization for the tiles have on the overall morphology? Let's try running another simulation where we assign all the tiles the same energy penalty and see what different morphology we get. So I've gone back to my input.txt. I'm going to change this to simulation number 2 for LTA, but I'm going to leave all the other parameters the same. So let's run this simulation, but assign different free energies of crystallization. So this time I'll say yes to the Q scaling, and I'll say yes to the tile scaling being the same too. And I'll assign all cages, or tiles, an energy scaling of 2.0 kcal per mole. And then I'll put the same parameters in for the other answers. 100,000, 500,000, find. So now simulation 2 is finished. We can visualize this with the CrystalGrower visualizer again. Follow the same steps to open the file. But we'll open file number 2 this time. And you can see how dramatic the morphology changes. So now we've got a really rough looking cube compared to what we had previously, which had lots of corner and edge facets. Now we've only got the 100 facets. Now just as an additional part to the video, I want to show you how to make movies when you're using the CrystalGrower Executable file. So in the user interface you specify the number of frames, which you can do down here, line 19. And you also specify the point at which you want to start capturing frames and when you want to stop capturing frames. So that's 20 and 21. So let's say, for example, I wanted to capture 50 frames of this simulation and I wanted to capture them in the last half of the simulation. I can change this to 500,000. So it's going to equally space 50 frames across this range of iterations here. I know this is separate to the other topic of the video, which is the free energies of crystallization, but this is one of the most crucial features you're going to use in CrystalGrower, and it's important to know how to use this just to study how the growth is affected by changing your free energies of crystallization. So let's run this simulation and see the output. So if we look at the file we've generated, we can see that the file is much larger. It's 90 megabytes roughly. So let's open this file with the CrystalGrower visualizer. We'll first open our data file, which is our LTA3. And then we'll open our coordinates data, which is LTA3 again. It'll take a few seconds to load the data in because it's bringing in multiple frames. But then a box will appear to tell you how many frames have been loaded. You can see we've got this small crystal shape, And if you use the arrow keys on the keyboard, you can scroll through and see how the crystal's growing over time. It won't be growing much towards the end because it's all under equilibrium, but at the beginning you can see the terraces growing quite quickly as it's reaching equilibrium. You can also open this in Avito, same as you can with the user interface. So if we double click that file, press OK, it's going to load all the frames from the directory, but if we only want to look at simulation number 3, you can just type 3 in here. And then we've got our 50 frames down the bottom there. So we can scroll through our frames and see the crystal growing the same as you can in the visualizer. So hopefully this video shows you how to change your free energies of crystallization for a net-based structure and a tile-based structure, and also shows you how to make movies for these structures, as the process works the same for tiles and net-based structures. In the next video, I'll go through adding additional crystallization features like screw dislocations and growth modifiers, and then we'll progress on to using the terminal for some shortcuts when running simulations with the standalone version of CrystalGrower, eventually leading towards using HPC systems like Condor or the CSF at the University of Manchester.